For centuries, man has used air as a means of power. The Dutch, for example, used windmills to reclaim much-needed land by pumping back the sea. Long before steam was harnessed as a power source, sailing ships relied upon air to open commercial sea lanes around the world. Today, in aviation, we not only use air as a means of flight, but for power to operate important instrumentation. These systems are known as pneumatic systems. They require periodic maintenance and careful adjustments to ensure efficient operation between inspections. For this reason, this specialized training program has been prepared to help you, the professional aviation maintenance technician, to better understand aircraft pneumatic systems and their components. Modern aircraft pneumatic systems evolved as a result of demands for a constant air source necessary to drive navigational, gyroscopic instruments, and many other aircraft systems. In the early days of aviation, this air source requirement was not nearly as important as it is today. The crude gyro instruments were simply spun by a stream of air flowing over buckets cut in a rotating wheel. In some models, airflow was accomplished by evacuating the gyro case by venturi tubes located on the outside of the aircraft. But when flying in adverse weather, these venturis were susceptible to icing, making them impractical for flight under conditions where these instruments were needed most. The first mechanical application of aviation pneumatics was the use of an oil-lubricated or wet pump. This unit used a small amount of engine oil, metered under engine oil pump pressure, to achieve its sealing and lubricating qualities. Once lubricated, the oil from these parts was discharged into an oil-air separator to prevent unsightly oil stains on the belly of the aircraft. This separator allowed the oil to flow back into the engine oil supply for recycling back through the pump. As the state-of-the-art in autopilots, de-icing equipment, and gyroscopic instruments advanced, an absolutely clean, oil-free air source was needed. In order to accomplish this with an oil-lubricated pump, additional oil-air separation devices were necessary, increasing the overall system weight. To avoid this problem and meet the demand for clean oil-free air, a new type of pneumatic pump, a self-lubricating dry air pump, was developed and is currently available from a number of component manufacturers. This new generation of dry air pumps eliminates the need for external oil separation devices, and rather than using steel vanes that rotate inside a cast iron cavity, these pumps employ carbon vanes sliding in a carbon rotor. These vanes wear constantly in microscopic amounts to produce the lubrication required. Many of these dry air pumps are bidirectional, meaning they can be operated either clockwise or counterclockwise. To accomplish this vane construction is much the same as an oil-lubricated pump, with the vanes radiating directly from the center of the rotor. On other types of dry air pumps, the vanes are canted into the direction of rotation. This allows the use of longer vanes, which reduces tip velocity to increase their useful service life. To maintenance personnel installing unidirectional pumps, it is extremely important to match the rotational direction of the pump with that of the engine drive pad. The direction of pump rotation is determined by simply looking at rotation of the drive pad, or by viewing the pump from the anti-drive end. With this new generation of dry air pumps, aircraft owners are often able to obtain a pump service life comparable to the total life of the engine. Maintenance costs are less, and greater reliability and air safety are also achieved. However, as aircraft began to fly at higher altitudes where the air is extremely thin, further changes in aircraft pneumatic systems are again necessary. To illustrate this, at sea level, a typical dry air vacuum pump has a compression ratio of 1.3 to 1. At 30,000 feet, however, its compression ratio is 4.5 to 1. Using the same pump, but as a pressure pump instead of a vacuum pump, its compression ratio at sea level is 1.23 to 1, as compared to 1.78 to 1 at 30,000 feet. In short, the lower compression ratio of a pump, the lower its operating temperature and wear factor. Based on this, pressure pumps at altitudes above 15,000 feet will last up to 30% longer. Since the only function of a pump is to move air, dry air pumps may be used in either vacuum or pressure systems. In both cases, the extremely close tolerances used in the manufacture of these pumps makes it imperative that oil, grease, or degreasing fluid not be allowed to enter these pumps. On vacuum installations, a polyurethane garter-type filter surrounding the regulator air inlet located out of the engine compartment prevents contamination from entering the system at this point. A central air filter mounted on an instrument's air inlet removes contaminants such as tobacco smoke before they can damage instruments or the pump. In pressure systems, the air comes from an area less susceptible to smoke and dirt, thus reducing the danger of contamination. These filter elements, however, should be replaced every 100 hours or as recommended by the manufacturer. After the air is regulated in a pressure system, it then passes through an inline filter that removes particles larger than 0.3 of a micron. Since the smallest object the human eye can detect is about 40 microns, this is indeed a very effective filtration system. In addition to filtration, the airflow produced by either a vacuum or pressure pump must be controlled. This is achieved by installing an adjustable flow controller. In a vacuum system, a relief valve is installed between the pump and instruments, so a constant low pressure or vacuum is maintained on the instrument side of the valve. This is accomplished by allowing filtered air to enter the system when the pressure is below that for which the valve is set. In a positive pressure system, the relief valve is located on the pump's discharge side. This maintains the proper pressure required by the instruments or other appliances. In this type of installation, air pressure from the pump acts on a preset diaphragm, opposing the force of an adjustable spring. Excess pressure beyond the regulated limits lifts the diaphragm and dumps it overboard. Another type of regulator used with dry air is the inline pressure regulator. Here, air pressure tends to seat a ball valve against the action of a spring. If the pressure rises above preset regulator limits, the regulator shuts off the line until the pressure drops. Both types of regulators operate smoothly and quietly. Some multi-engine aircraft using de-icer systems have another type of pressure regulator that constantly provides regulated air pressure for the pilot's gyro instruments. In these applications, when high pressure is demanded for de-icer boots, a solenoid valve momentarily shuts off airflow to the co-pilot's gyro, permitting the maximum volume of air to enter the de-ice system. As soon as the pressure in the boot rises to its required level and deflation occurs, this air is then redirected to the gyros. The interruption is so short, instrument operation is not affected. Two-stage pressure relief valves used by many twin-engine aircraft maintain a low pressure setting to the gyro pressure regulator. When the solenoid on the relief valve closes off the low pressure side, the pressure then rises to the level required by the de-icer boots. A second valve, the primary relief valve, maintains air pressure to the gyro instrument regulator. Generally, this is about 5 psi. When maintaining aircraft pneumatic systems, a good rule of thumb to remember is that pressure alone does not determine the speed at which the rotor of a gyro spins. This is the job of the airflow, which may be indicated by the differential pressure across the gyro. A standard suction gauge, for example, measures only the difference in air pressure inside the instrument case and the outside air. While it provides a good indication of what the regulator is doing, it tells nothing about the amount of air flowing through the instrument itself. If a filter clogs or the line from the filter to the instrument becomes pinched, the suction gauge will give no indication of trouble. In fact, the reading may be even slightly higher than normal. A standard pressure gauge will give the same misinformation. A clogged system can restrict the airflow, but as long as the regulator functions properly, an indication of sufficient pressure will be seen. The differential pressure gauge used in either a vacuum or pressure system gives total information as to the airflow through the instrument. The pressures of the instrument inlet and outlet are compared, and if the airflow is restricted into or out of the instrument, the differential pressure will be noted. Since the main function of an air pump is to move air, anything that restricts this flow of air causes the pump to work harder, generating more heat. The restricted flow also deprives the pump of the cooling air it needs, thus shortening its service life. To assure that the airflow through the system is not restricted, use only fittings and lines of the proper size and design. AN fittings are commonly used in fluid lines. However, their thick walls produce restricted bores, and the fluid flow through them must turn at right angles, creating back pressure or turbulence. The use of an AN elbow will often produce a pressure drop equivalent to 10 feet of the same size tubing. In comparison, low-loss fittings have thin walls and swept corners. This eliminates turbulence within the fitting. Used consistently, these fittings will keep pressure drops in the system to a minimum. In addition, the hose from the pump to the vacuum relief valve in a vacuum system should be no smaller than 5/8 inch inside diameter. If the gyros are connected in parallel, each gyro should have a 3/8 inch inside diameter connecting line from the central filter and to the relief valve. In a vacuum system, never use a hose less than 5/8 inch inside diameter between the pump inlet and vacuum relief valve. When driving two gyros in series, always use a 1/2 inch inside diameter hose from the relief valve to the artificial horizon first. Then a 3/8 inch inside diameter hose between the artificial horizon and directional gyro. In multi-engine installations, both vacuum pumps feed into a common manifold. This manifold has two check valves connected by lines to the source indicators on the differential pressure gauge. Both pumps supply the system. However, in the event one air source fails, it will be shown by the source indicator. Movement of a large volume of air under an appreciable pressure requires a great deal of work, resulting in the generation of heat. In larger output systems, these pumps must be additionally cooled by directing a blast of air over their finned surface. In conclusion, the air used in aircraft pneumatic systems must be filtered. This air is moved by pumps and controlled by regulators. In this way, it operates our highly complicated gyroscopic instruments, autopilots, and de-icer boots to allow flight in adverse weather. Careful maintenance and inspection of these systems are important in order to achieve maximum service life and performance. The preceding presentation has been an introduction to basic aircraft pneumatic systems. Since it is your responsibility as a professional aviation maintenance technician to keep these systems at their peak operating efficiency. Part 2 of this presentation will deal with the entire pneumatic system, its maintenance, and troubleshooting. Part 1 of this presentation reviewed the various components of basic aircraft pneumatic systems. We are now ready to discuss the general requirements of the entire pneumatic system, its installation and troubleshooting. Since the pump is the heart of a pneumatic system, we must clearly understand how it functions to service the system effectively. Often, a pump will fail because it has been overloaded or overworked, rather than through any fault of the pump itself. For this reason, air pumps are rated according to their capacity and differential pressure. No pump should ever be installed in a pneumatic system whose requirements exceed the limits of the pump. Never add equipment unless approved by the airframe or pump manufacturer for a particular installation. And do not modify any system without first determining if the total air load is within the operational capability of the pump. If pump failure should occur and replacing the pump does not improve the condition, most likely the pump is not at fault. It is usually another component within the system or the design of the system itself. To determine the cause of difficulty, rather than continually change parts, the service department of the manufacturer should be contacted immediately for a recommended course of action. Dry air pumps are precision components that must be matched to the system. To determine the right pump configuration, refer to the airframe manufacturer's parts catalog, bearing in mind that often bulletins may be issued by the manufacturer to change a specific model. During installation, special care must be taken when handling the pump itself. If dropped, its carbon rotor and vanes could crack, causing the pump to seize. Caution: never return a pump to service if it has been dropped. When installing the pump, do not clamp it in a vise with the jaw across the pump body, as it could cause the carbon rotors and vanes to crack. To install the fittings in the pump, hold it in a vise across a mounting pad using either wood or soft metal jaws in the vise. Low-loss fittings are usually recommended during installation because AN fittings, with their smaller inside diameter and sharp corners around which the air must travel, have a more restricted flow. A small amount of silicone or moly-sulfide spray on the male threads will serve as a lubricant for installation. Anti-seize compound or Teflon tape should never be used, as a small amount could enter the pump and cause severe damage. Screw the pump fittings in until hand tight, and then with a box end wrench, tighten them until proper alignment is reached, never more than 1.5 turns beyond hand tight. Check the condition of the pump drive oil seal in the engine, and if there is any leakage, replace it. The drive end of the pump must be protected from any contaminants such as oil or solvent. A common practice in the field is to replace this seal each time the pump is replaced. Prior to installing the pump in the engine, determine if the pump will turn without binding or in a lumpy manner. Now, using a new gasket, install the pump on the drive pad, mounting it in the position that provides best clearance for the attached lines. Using the proper washers, lock washers, and nuts, torque the attached nuts uniformly from 40 to 50 inch-pounds. After the pump is installed, connect the hoses, being certain that they are perfectly clean inside, free from any oil, solvent, or foreign debris. Be sure that the hose laminations are not separating, as sections or pieces of the hose are instant death for the pump. When washing an aircraft engine down with degreasing solvent, gunk, or water, it is advisable to place a shop cleaning rag over the mounting flange area of the pump, that is, the area where the coupling is visible. This will prevent accidental forcing of the cleaning solvents or gunk into the working parts of the pump, which would cause serious damage to the carbon-moving parts. Also, if the hose has been removed from the inlet fitting, protect this opening with a plastic stop or plug to prevent foreign matter from entering the system. Operational speed is one of the factors that determines the service life of an air pump. Some engines have pump drive pads with a speed of 1.5 times faster than engine speed, while in others the speed is the same as the crankshaft. Keep in mind, the slower the pump rotation, the longer its service life will be. This is an important point to remember. Service life of a pump is directly proportionate to the load it carries. And since the technician controls the load placed on the pump, he also is responsible for the length of its service life. Another probable cause of short pump life is an overload caused by airflow obstruction. This is often due to a faulty or plugged filter within the system. In a vacuum system, replace the air filter every 500 hours or more often if the airplane is operated in extremely dusty conditions. The foam garter-type filter on the vacuum regulator should be replaced every 100 hours of operation, and again, in the event of dusty conditions, more often. In a pressure system, replace the pump inlet filter each 100 hours. The 3/10 micron inline filter, located at the inlet to the gyros, should be replaced after 500 hours. In the event of pump failure in a pressure system, be sure to replace the inline filter as well as the pump. The reason for this is the possibility that small, sharp carbon particles from the old pump could be discharged into the system, and with vibration and time, the particles could cut through the paper filter element and cause damage to the gyros. Aside from routine filter replacement, these filters should also be replaced in the event of a gyro malfunction or any indication of pressure drop on the differential pressure gauge. Keep in mind, a standard vacuum gauge cannot indicate the condition of the filter. If a pressure drop is noted or a gyro appears malfunctioning, check for a clogged filter before attempting to adjust the pressure regulator. Also, check for pinched lines or obstructions in any of the airflow lines. If a regulator adjustment to correct a pressure drop is made improperly, or an adjustment made when the real problem is due to obstructed airflow, the pump will be unnecessarily overworked and its life will be shortened. In modern pneumatic systems, both the vacuum and pressure regulators are quiet operating and trouble-free. Once they've been set, do not readjust them unless absolutely certain the regulator is at fault. To make the initial adjustment on a vacuum regulator, unlock the adjustment screw and turn it clockwise to increase the suction. Set it to the value recommended by the airframe manufacturer and relock it. When installing or troubleshooting a pressure autopilot system such as a Britain, first set the regulator to the pressure required for the autopilot. This is usually around 5 pounds per square inch. Then, adjust the gyro instrument regulator to the required pressure. This is usually around 2.7 pounds per square inch, but always use the specifications of the airframe manufacturer. If a range of pressures is allowed, set the regulator to the lowest level. This will aid in maintaining longer service life of the pump. By using low-loss fittings throughout the system and installing only approved filters, pump life will be further increased. Never use a line with an inside diameter of less than 5/8 of an inch between the pump and the regulator. When driving two gyros in series, use a line no smaller than 1/2 inch in diameter connected to the artificial horizon, and if only one gyro is to be driven, a line no smaller than 3/8 inch should be used. The inlet and outlet lines of all instruments must be of the same size, unless you are increasing or decreasing volume from another instrument. And any hose that has become hard, has developed cracks, or starts separating should be replaced. Twin-engine aircraft use a central manifold and check valve assembly, through which both pumps are connected to the gyros. In the event of an air source failure, one of the check valves will isolate the inoperative part of the system, allowing the remaining pump to carry the load. A source indicator in the aircraft panel gauge will show a red button to indicate which source is out. Modern pneumatic systems provide the muscle for autopilots and de-icer systems, as well as the air power for the gyros. Careful maintenance of these systems will aid in preventing leaks or obstructions that could shorten the service life of the air pump. For you, the professional aviation maintenance technician, to be capable of effectively maintaining these systems, you must have an intimate knowledge of their operation. It is hoped that with the specialized aviation maintenance training program, you have gained a greater insight of the aircraft pneumatic system and its many components.